Welcome to week 2 of Fundamental of Python and Machine Learning. In this lesson, we are covering the chapter 2, Extending Python using NumPy, from the Python Machine Learning by Wei-Meng Lee book. So last week, we introduced the basic idea of machine learning and reviewed the Python working environment. This week, we're moving into one of the most important tools for working with data in Python, and it's called NumPy. NumPy stands for Numerical Python, and is one of the core libraries used in data science, artificial intelligence, and machine learning. Many libraries that we will use later, including Pandas, Scikit-learn, and other data science tools, are built on top of NumPy. So, or use a NumPy-style data structure. The main question for this chapter is simple. How can Python handle large amounts of numerical data efficiently? That's where NumPy becomes important. By the end of the chapter, you should be able to do 5 important things. First, you should be able to explain what NumPy and why it is useful. Second, you should be able to create NumPy arrays from a list of built-in NumPy functions. Third, you should be able to inspect arrays by checking their shape, size, dimensions, and data type. Fourth, you should be able to access values inside arrays using indexes and slicing. And fifth, you should be able to perform mathematical operations on arrays without writing long loops. These skills might be seen basic at first, but they are extremely important. In machine learning, data is often represented as numbers. Those numbers might represent grades, price, temperatures, image, text features, student records, business transactions, or even medical measurements. Before we can train a machine learning model, we need to organize that data in a format that the computer can process. NumPy helps us do exactly that. Python already has lists, so a common question will be, why do we need NumPy arrays? A Python list is very flexible. It can store numbers, a string, objects, and even other lists. That flexibility is useful, but it also makes the list slower and less efficient for numerical computing. Machine learning often requires many calculations over large datasets. For example, we might need to add thousands of numbers, multiply matrices, calculate average, or compute values across many rows and columns. Using regular Python lists for this type of work can become slow and harder to manage. NumPy arrays are designed especially for numerical data. They are faster, more memory efficient, and allow us to perform operations on entire groups of values at once. For example, with a regular Python list, if we want to multiply every value by 2, we usually need a loop. With NumPy, we can multiply the entire array by 2 in one line. This is one of those biggest advantages of NumPy. It allows us to think in terms of whole arrays instead of one value at a time. The most important object in NumPy is the array. A NumPy array is a structured collection for values, usually numbers. You can think of it as a container that stores data in a way that is efficient for mathematical operations. And one-dimensional array looks like a simple list of values. For example, Python 10, 20, 30, or 40. This could represent test scores, ages, prices, or any sequence of numerical value. A two-dimensional array looking more like a table with rows and columns. For example, we have 10, 20, 30 as a section, to 40, 50, 60, and then 70, 80, 90. This structure is important because most real-world datasets are organized like tables. Each row might represent one record, such as one student or one customer. Each column may represent one feature, such as age, score, income, or number of purchases. In machine learning, this is a very common. We often store our input features in two-dimensional arrays, where rows are examples and columns are features. Before using NumPy, we need to import it in our Python program. The standard way to import NumPy is import NumPy as NP. The name NP is an alias. It is a shortened name that programmers commonly use when working with NumPy. This means that instead of typing numpy.array, we can type np.array. This is not required, but is one of the standard conventions used in most Python, data science, and machine learning examples. So when you see np, you should immediately recognize it as one that refers to NumPy. The simplest way to create a NumPy array is by converting a Python list into an array. For example, We can have scores equals NP array 85, 90, 78, 92, 88, and then print those scores. This creates a NumPy array containing 5 test scores. We can also create a two-dimensional array by using a list of lists. So we have grades equal NP array, and we have 85, 98, 78, 92, 88, 95, and 76, 84, 80. Here, we have 3 rows and 3 columns. This should represent 3 students and 3 assignments. NumPy also provides a function to create arrays quickly. For example, np0s 5 creates an array of 5 zeros. np1s 5 creates an array of 5 ones. np arange 1 to 10 creates a sequence of number from 1 up to, but not including, important, 10. And at the end, np linspace 105 create 5 evenly spaced values between 0 and 1. These functions are very useful when we need to initialize data, create ranges, or prepare values for calculations. After creating an array, we often need to understand its structure. NumPy gives us several useful properties. The first one is shape. The shape tells us the number of rows and columns in the array. For example, if result is 3 over 3, that means the array has 3 rows and 3 columns. The next property is size. The size tells us the total number of elements in that array. If we have 3 rows and 3 columns, the size is 9 because there are 9 total values. Another important property is ndim. Ndim, what it does, it tells us the number of dimensions. And one-dimensional array has 1 dimension. A two-dimensional array, of course, it has 2 dimensions, and go on. Finally, we can check data type using dtype. The dtype tells us what kind of values are stored in the array, such as integer or floating point number. This matters because machine learning models accept numerical data, and different numerical types can affect memory usage and calculations. Indexing means accessing a specific value inside the array. In Python, indexing starts with a 0. This means that the first item is index 0. The second item is index 1, and so on. If we want the first score, we use the name of the variable and the number of the index between square brackets. So if we have a score NP array 85, 90, 78, 92, 88, score 0 returns 85. If we want the third one, we use scores 2. This returns 78. For a two-dimensional array, we need to specify both the row and the column. So an NP array of 3 different values. To access the value in the first row and the second column, we use grade 0, 1. And this will return 90 in this case. The first number represents the row index. The second number represents the column index. This is very important when working with datasets because we often need to access specific rows, columns, or values. Slicing allows us to select a range of values from an array. For a one-dimensional array, we can use the syntax scores 1, column 4 to return the value starting from index 1 and stopping before index 4. So if our array has 5 values, 85, 90, 78, 92, and 88, the scores 1 to 4 returns 90, 78, and 92. The starting index is included, but the ending index is not included. For two-dimensional arrays, slicing becomes even more powerful. For example, grades, column, comma 0. This selects all rows from column 0. In other words, it selects the first column. The column means select everything in that dimension. So grades, column, comma 0 means select all rows, but only the column 0. Another example will be the other way around. Grades 0, comma column. This means select row 0 and all columns. Understanding slicing is very important because in machine learning, we often need to separate input features from output labels. For example, we use some columns and the data model learns from, and another column as the value that we want the model to predict. Reshaping means changing the structure of an array without changing the actual data inside. For example, numbers NP-arange 113 is creating an array with numbers from 1 to 12. Right now, it's a one-dimensional array. We can reshape it into 3 rows and 4 columns. Numbers.reshape 3, 4. The result will be a multi-dimensional array with the separation of 4 values each one. The important rule is that the total number of elements must match. If we have 12 values, we can reshape them into 3 by 4 because 3 times 4 equals 12. We could also reshape them into 2 by 6 or 4 by 3. We cannot reshape 12 values into 5 because 5 will be require 25 values. In machine learning, reshaping is common because models often expect data in a specific format. One of the main reasons NumPy is powerful is that it allows us to perform mathematical operations on the entire arrays. For example, NP array 85, 90, 78, 92, and 88, we want to add 5 points to every score, we can write score plus 5. NumPy automatically adds 5 to every value in the array. If you want to multiply every score by 2, we can just write scores by 2. This is called vectorized operation. A vectorized operation means the operation is applied to the entire array without writing a manual loop. NumPy also provides useful mathematical functions. We can get the mean, calculate the average, max to find the highest value, min to find the lowest value, sum to add all values together. These operations are very useful in data analysis. Before training a machine learning model, we often need to understand the basic statistics of our data. Another important NumPy concept is broadcasting. Broadcasting is NumPy ability to apply operations between arrays of different shapes, as long as they are compatible. A simple example is adding one number to an entire array, as we saw before, like score plus 5. This number 5 is treated as if it were available for every value in the array. This is broadcasting. Another example, if we initialize a price array with 10, 20, and 30, and we have a taxes equal 1.025, we can do final prices equal to prices by tax. Here NumPy multiplies each price by the tax value. Broadcasting helps us avoid unnecessary loops and make us code shorter and easier to read. In machine learning, broadcasting is used often when scaling data, adjusting values, applying formulas, or performing calculations across features. One concept students should be careful with this array assignment is we create an array and assign it to another variable, like a equal NP array 1 to 3, and then b equal to a. We might think we create a new copy of the array, but in many cases, b is not a separate copy. It's another reference to the same array. So if we change b, we may also change a. For example, b0 equal 99. Now the first value of a may also be changed. To create an actual copy independent, we should use the copy command. This matters because when working with data, we do not want to accidentally change the original dataset. A good habit is to use the copy command when we intentionally want a separate version of our data. Now let's connect this chapter to machine learning. Machine learning models do not understand data that humans do. A human may look at a spreadsheet and understand that one column represents age, another column represents income, another column represents category. But a machine learning model needs the data to be covered into numbers and organized into arrays. For example, imagine we are building a model to predict whatever a student may need academic support. The dataset may include values such as hours studied, attendance percentage, previous exam score, assignment average. These values can be organized into a NumPy arrays. Each row represents one student. Each column represents one feature. This machine learning model uses those numbers to identify patterns. This is why NumPy is so important. It gives us the structure needed to prepare data before we train models. Later in this course, we'll use Scikit-learn. Many of the inputs and outputs will look like NumPy arrays. So, even we are not building a machine learning model yet, we are learning the foundations that make machine learning possible in Python. Let's look at a simple example. Suppose we have a student score for 3 assignments, as you can see right now in the screen. Each row represents one student, each column represents one assignment. We can find the average score for each student using the mean. The axis equal 1 means we are calculating across the column for each row. We can also find the average score for each assignment with the axis equals 0. The axis equals 0 means we are calculating down the rows for each column. This is example shows us arrays are useful. We use a few lines of code, we can summarize data and identify patterns. For example, we could ask which student has highest average, which assignment has the lowest average. Are scores improving from assignment 1 to assignment 3? These are basic data analysis questions, but they are also the beginning of machine learning thinking. Before we train models, we first need to understand the data. Before we finish, let's review some common mistakes students make when learning NumPy. The first mistake is forgetting that indexing starts at 0. The first item is index 0, not index 1. The second mistake is confusing rows and columns. In a two-dimensional array, remember that the array starts with row and then with a column. The first value is a row and the second value is the column. The third mistake is reshaping the array into incompatible shapes. The number of elements must stay the same. The fourth mistake is assuming that assignment always create a copy. If you need a separate copy of an array, use the copy command. The fifth mistake is trying to use Python loop for everything. NumPy is powerful because it allows vectorized operations. Try to use array operations whenever possible. These mistakes are normal when you are learning, but being aware of them will help you write better code. Let's summarize what we covered in Chapter 2. NumPy is a Python library used for numerical computing. The main object is NumPy is the array. Arrays can be one-dimensional, two-dimensional, or even higher dimensional. We can create arrays from Python lists or using NumPy functions such as zeros, ones, arange, or even linspace. We can inspect arrays by checking their shape, size, number of dimensions, and data types. We can access values using index and slicing. We can reshape arrays when we need the data in different structures. And we can perform mathematical operations of entire arrays using vectorized operation. Most importantly, NumPy prepares us for machine learning because machine learning models work with numerical data arranged in structured formats. For this week, your goal is to practice working with NumPy arrays. You should be able to create arrays, inspect the structure, access specific values, slice rows and columns, reshape arrays, and perform basic calculations. As you complete the assignment, don't just focus on getting the code to run. Try to understand what the array represents. Ask yourself, what does each row represent? What does each column represent? What calculation am I performing? How could this help prepare data for machine learning? In the next chapter, we will move from NumPy arrays into pandas, where we will work with tabular data using data frames. Pandas will make it easier to load, clean, and analyze real datasets. But NumPy is the foundation. If you understand arrays, indexing, slicing, reshaping, and array math, you will be better prepared for the rest of the course.